And we will continue with Kai Meinerz from the University of Cologne. Thanks for moving up in the schedule. So as I said, he's doing his PhD at the University of Cologne in the group of Simon Trebst, and he worked on topological surface codes. But today he will talk about the quantum cartpole.
This one is to switch the slides. That's just a laser pointer.
So two different, okay.
Yeah.
As long as it works. Yeah, thank you for the nice introduction. I am here today to talk about applying machine learning to quantum control. Oh, there you go. And using the example of the Quantum Cartpole. This project has been a cooperation between the University of Cologne and the Niels Bohr Institute in Copenhagen, and I was working with Evert van Nieuwenburg. So sadly he couldn't make it today, but that happens. And, for the motivation, quantum control has been a topic of increasing interest over the last years. One of the reasons being it's a key component for quantum computing, because let it be like the noisy intermediate scale quantum computing or the large scale quantum computing we want at the end, we need quantum control to stabilize the system over an extended period of time. And as it turns out, the model-free algorithm seems to be a good candidate for those control algorithms, since they seem to be tolerant against experimental noise. And since reinforcement learning is one of those model-free algorithms, our idea was to build like a simple quantum environment which can be used to benchmark different agents and policies in order to create some quantum control algorithm. And for this, we took some inspiration from the classical example of the cartpole problem. This is basically the problem of like balancing a pen on top of your hand, which I cannot do. And the agent controls basically the card at the bottom and tries to balance this pole on top of it. And in order to take this to like a quantum problem, what we did, he put a wave function inside of a potential. Our wave function here is now the card and the pole at the same time, and the potential is basically the external constraints. As long as we have like this parabolic potential or harmonic potential, our wave function will stay safe in the middle of it, which is a bit boring. So what we're gonna do is we will flip the potential, turn it upside down, and then our wave function will start to move to one of the sides of the potential. It will start dropping out. And as soon as the peak of the wave function goes by one of the thresholds we defined, those are those black bars, because we will consider it basically game over, and therefore we have to start from the beginning. So in order to avoid that, we will perform some measurements of the wave function to get some information about the position and momentum of the wave function. These information will be fed to a reinforcement learning agent, which will then decide to apply a kick operator, basically to apply a force which will or should push the wave function back to the middle. But it's not as easy as it sounds, because there are two problems we are facing. First of all, we have the general problem of the uncertainty principle, which tells us that the position and momentum are given by Gaussian distributions. And the standard deviation of those distributions are related by the uncertainty inequality, which just tells us the product of both deviations is bigger or equal to h bar half. And which just means that if we have like a sharp position distribution, we will have a wide momentum distribution. And the other way around, if we have a sharp momentum distribution, we will have a wide position distribution. This is a fundamental property, quantum property, and not a statistical problem. So independent of what kind of measurement we perform, we essentially deal with noisy data. And second problem is if we just place our wave function on top of this inverted potential, what's going to happen? It will delocalize over time. So On the top, we have the probability distribution of the wave function. On the bottom, we have the real and the imaginary part, and you can see it just spreads out over time. So what we want to have is that the wave function remains at a constant shape over time. So we need some method which causes the wave function to contract over time. And for this, we apply weak measurements to the system. And the weak in the measurement here means we don't measure on top of our system wave function directly. Instead, what we're going to do is we couple the wave function with another different and ancillary wave function over a short period of time and perform measurement on that wave function instead. From this, we can learn some information about the momentum and potential position of the system wave function while keeping our wave function safe and not causing it to collapse by some direct measurement. And additionally, we do exert some influence on top of our system wave function, which will cause the wave function to contract and also slightly be displaced. So if we apply these weak measurement, you can now see that the probability distribution is able to retain a constant shape over time. The width of the distribution actually depends on the parameters of the weak measurement, so this is something we can control. And additionally, you can see it also starts wiggling around a bit, which is also caused by the displacement of the weak measurements. So now the only problem we have to solve is how to keep the wave function stable in the middle, since it still drops out to the side. And with that being said, we can start to build the environment for our reinforcement learning agent. And for this, we basically created two loops. First, we have our time loop of the length dt, where we perform 4 different things. First of all, we apply a kick operator to our wave function, which is decided by the reinforcement learning agent and should cause the wave function to go back to the center of the potential. Then we have the time evolution of the wave function in the potential, which causes the wave function to spread out over time. And afterwards, we have the position and the momentum measurement, and which will cause the wave function to contract again and also slightly be displaced. And we get some information about position and momentum. And this loop, we will just repeat an arbitrary amount of times, which we will choose beforehand. And after that, we will take all the different position and momentum measurement, take the mean value, and feed it to our reinforcement learning agent. For those who are interested, the agent we have used was a PPO model, just out of the box, so there is no thing special here. And the agent will then decide what kind of direction and strength to choose for our force. And then we just adjust our kick operator, and we can start the whole thing from the beginning. And what is really nice about this setup is that we now basically have a way to tune this environment from a completely quantum environment to something which is closer to a classical environment. Because if we only perform a single measurement before giving the data to our reinforcement learning agent, we have maximum uncertainty in our data, and we are basically the complete quantum regime. But if we perform a large number of measurements in a short amount of time, we get a better estimation of our actual momentum position, and we will get closer to this classical Cartpole problem, since we have just better information. So with this, our environment is basically done. We can perform some training just to keep the wave function as long as possible inside the thresholds. And once that's done, then the results will look like something like this. You can see now that our agent constantly applies and adjusts the force to our wave function. The black arrow depicts the force, and the size of the arrow actually correlates with the strength of the force, and it seems like our agent is successfully able to keep the wave function inside the thresholds. But let's have a closer look at what our agent actually does. For this, we can look at the right graph. On the x-axis, we have the position of the peak of the wave function, and on the y-axis, we have the time passed and time steps dt. And it seems like our agent is actually not that good in keeping the wave function in the center of the potential. Instead, what it does is, as soon as the wave function goes like far away from the center, it will push it back. And often it seems like it even overcompensates, causing the wave function to go in the other direction and then needs it to bring it back again. And so there's still some improvement which could be made. And additionally, we want to look at how does the performance scale with the number of measurements. And here in the graph, on the x-axis, we have the number of the weak measurements we perform, where one constitutes to a single position and momentum measurement. And as we said before, with a single measurement, we are in this quantum regime, and we go up to like 20 weak measurements before giving input to our reinforcement learning agent, which would be closer to the classical regime. And on the y-axis, we have the average time until our wave function drops out of the system. For comparison, we added this orange line, which is how long our wave function stays inside. If we apply no control actions, then it will drop out in roughly 300 time steps, so pretty fast. And as soon as we apply some controls, the lifetime goes up immediately. For a single measurement, we have an increase in lifetime by a factor of around 90. And if we increase the number of measurements, it goes immediately up to a factor of 800 by around 4 to 6 weak measurements. And this increase in performance we can simply explain by performing more measurement. We have a better idea about our data. We reduce the noisiness effectively, and our reinforcement learning can decide more accurately what kind of action to take. But after 4 to 6 measurements, the performance starts to drop again. And this we can explain by an increase in latency, because with every single measurement, we do have some time evolution of our wave function, meaning it will start dropping out of the bounds. And if we just measure way too long, our wave function will already be on its way out before we react. So there's definitely some kind of trade-off between how many measurements you want to perform and when you want to react. And with this, let me quickly conclude. What we did is we connected reinforcement learning with basic quantum control. We built a simple quantum benchmark environment based on a classical environment, and we stabilized the wave function inside an inverted potential for the quantum and the classical regime. And with this, I want to thank you all for your attention, and I'm at the end.
Thank you very much. Thank you very much for the nice talk and the nice animations. Are there any questions? Yeah.
I guess you don't have an experimental embodiment of your experiment. What would stand in
not,
the way?
Not yet. Not yet.
What would stand in the way of actually realizing such a system?
Currently finding the experimentalist who's willing to do it. But we have some plans of maybe like stabilizing a quantum dot in a potential to test it out on an actual experiment. But we are still looking for a group to cooperate with this, since I'm not allowed to go near any experimental hardware.
The weak aspect of the measurements, this is something that could be achieved.
Yes. Weak measurements are already performed in many experiments, and we did choose those weak measurements because they could be realized in experiments.
So you mentioned that you were considering different ways of rewarding the agent in such a way that the mean position of the wave function doesn't fluctuate too much. Can you maybe tell us a little bit more about that? Like, have you tried something like also penalizing the variance of the position and
yes.
et cetera?
If we took the standard wave from the classical Cartpole, we just rewarded always the same amount as long as it's inside the thresholds, which is exactly what we are currently doing. But we also tested out for increasing the reward the closer you are to the center, and giving a harsher penalty if you drop out. This actually didn't lead to any improvement in performance in our case, which is probably because in this setup the agent has a really difficult time to decide if it can trust the data if the wave function is close to the center, because it can't really decide is it on the left or the right side of the potential.
Thanks. And another question, if I may, just real quick. So on the previous slide or so, you mentioned that there's weak measurements. There could be a position weak measurement and momentum weak measurement, and you put them in this order. Have you tried reversing the order? Like, would that make any difference?
We have tried inverting the order, but this doesn't really make a difference. The time scale is pretty short, so numerically there is almost no difference.
Okay, thanks.
Thank you a lot for the talk. I hope that this question is not too specific, but have you thought about how that a classical agent could have a disadvantage handling with this kind of environment with respect to a quantum agent, whatever we want to define it, or something that uses quantum circuits for the learning?
Yeah, definitely. So we did expect that classical agents have some problem with it, which is probably also the reason why the position varies so much, but we haven't had the chance yet to try any quantum reinforcement learning on top of it. But this is definitely something we want to test out maybe in the future to make a comparison.
Thanks.
Thank you for the talk. I was wondering if you could make a variation of this experiment with something like a nonlinear Schrödinger equation. So for example, using solitons. If you would have, for example, an attractive interaction in your Schrödinger equation, you could have a compensation of the dispersion of the wave function. So by tuning this attractive interaction, you could do something similar. Maybe it's harder to realize in experiment, but that's just something you could think of.
Yeah, I think that's definitely something one could realize.
It's just maybe a crazy idea, but this whole thing made me think about solitons for some reason. So I don't know. We can rediscuss.
Yeah, gladly.
Are there any more questions for Kai? Doesn't seem to be the case. Then let's thank him again, and in fact all the speakers of the session.